And hi, welcome. So this is lecture 7, rather rambling number 7. I'll just call it lecture to give it some semblance of dignity. Lecture 7. Okay, so we'll just pick up where we last left off and I'll kind of wing it as we go through. Yeah, I'll wing it. So last time we were talking about the implications of Schrodinger's equation. We get discrete energy levels. We have quantum tunneling. We have in the 3D version, we have important quantum numbers besides the energy level. So the principal quantum number n that will determine the energy level. L will represent the angular momentum. M will become the angular momentum projection. Okay. The other thing is that you also find that m is representing the orbital angular momentum number. So you'll see it right here under orbital magnetic dipole moment of the electron. Yeah, I just uploaded, or rather, I'm going to upload these sets of notes for you, plus the references. Okay, this is the spherical harmonics part. Now keep adding things on as we go. So yeah, let me do this. I'll just add all this on git add commit. Okay, added m is the orbital magnetic magnetic orbital quantum number. Right? Yeah, push it up on to GitHub, and yeah, so you'll be able to find all the notes there on GitHub under the physics section. Okay, so if you look at the file structure, there'll be one part called early lectures, which is what we are now. We have a physics and then templates. Okay, so the notes will be, at least these notes will be here under the physics folder as of now. I hope I try not to change. Okay, but okay, this is how it's structured right now. You'll be able to see all the links that I use under here. I used types, but you can just open the PDF file and you click this thing, it will bring you to the relevant websites, just like what is happening now. Okay, so the Schrodinger equation is here. You will be able to see it. Okay, so let's so all this is uploaded now on GitHub. You'll be able to see it. And now we will go to our next topic. Okay, so we previously talked about the different energy levels, and we used this guitar string analogy. Okay, so possibly at your lowest energy level, your wave could look like this. Okay, your wave function. Okay, or wave function. Okay, psi can look like this. Maybe n equals to 2. You have something a little bit different. Maybe this sort of sine, this sine-like wave with exponential decay outside. Yeah, so these are some common shapes. Okay, some common shapes. Now, for this, the lambda at n equals to 2 is shorter than lambda at n equals to 1. Okay, so the wavelength at this n equals to 2 is smaller than the n equals to 1. What it also means based on the equations, we call the de Broglie wavelength equation. Okay, lambda equals to h over p. It basically says the higher your wavelength, the lower your momentum, and vice versa. So basically, n equals to this wave, so to speak, has a higher momentum than the n equals to 1. Okay, so that is what we expect. In other words, we are saying that the energy at n equals to 2 is more than the energy at n equals to 1. Same idea qualitatively. So let's say for the most simple hydrogen atom, right? Hydrogen atom is the most simple. The shapes of the orbitals we talked about before. This is the s orbital. Okay, s orbital, and then the p orbital looks a bit like a dumbbell. Yeah, dumbbell. Now the infinity shape or looks like an 8 shape. This is a p orbital. a p orbital. Okay, so these are electron cloud shapes, electron cloud shape. And why am I talking about electrons now? Because there's a parallel going on in the nucleus. Okay, so a lot of these principles apply over to nuclear physics as well. So this s orbital has a low n number, or maybe a 1s. Okay, this one is the n right here. S will kind of correlate more to the orbital magnetic moment. This is the L number. Okay, so at n equals to 1, there's only this way it can vibrate. Okay, L equals to 0 right here. That's what S means. Okay, means we don't really have much in the way of angular momentum. But once you start going on to n equals to 2 and above, you will have even more ways to arrange your angular momentum thingy. So this P is basically saying L equals to 1. Okay, and S, I mean the N should be greater than 1. Usually that's the case. I hope this is not alien to you. We talked about this N, L, and M, but I mean, like it or not, this is the language we will deal with in a lot of quantum mechanics. Well, basically, it means the shape of the wave and the way things are like that. They are different. Okay, the way we like to differentiate them is using these quantum numbers. Okay, that's all. Right. So in the same way that this n equals to 2 wave is more energetic than this n equals to 1 wave, same thing, this p orbital thing is actually more energetic than this s orbital. Okay, because usually p is only available when you have n equals to 2 and upwards. Right? So that's the basic idea. Okay. So how do you how do you get from this S to P, or vice versa? Okay, you basically have different energy levels, right? You have different energy levels within the hydrogen atom. Okay, between n equals to 1 and n equals to 2, yeah, you can actually sort of transit between these two states. Okay, so basically, if you supply energy to the electron cloud, you can actually excite the electrons. So this is called excitation. It's excitation. So you basically supply energy to the atom, okay, the hydrogen atom in this case. You can sort of excite this electron cloud. Okay, of course, your energy supply must be greater or equal to, ideally equal to this amount right here, to excite it from n equals 1 to n equals 2. So the electron was basically here at this energy level. Supplying energy would actually change the shape of the wave, electron wave, and promote it to another energy level right here. Okay, so this is the n number. And at the same time, if you have excited state of electron, and you somehow leave it alone for long enough, it will de-excite itself and release energy. Okay, so this is called de-excitation. And yeah, this excitation and de-excitation is very important in both chemistry and nuclear physics, whether it's talking about electrons or protons de-exciting themselves. Okay, the physics behind them, it's pretty similar. Okay, the principles behind them. Okay, excitation, de-excitation. So when you have electrons, when you have excitation process, how does it happen? Right? One of the ways it can happen is you have light. Okay, you have light that comes in, and it will promote the electrons. Okay, so this is light. It's a part. It can be thought of as a particle or wave, but in this case, it's useful to think of it as a particle, right? So this light particle will come in, it will meet this electron, and then it will, it will transfer its energy to the electron, and then the electron will be promoted to a new energy level. So this is excitation. Okay, and when you have a de-excitation process, you actually release light. Okay, and then the light will be light energy equals to the difference between these two energy levels. Okay, so E at the n equals to 2 minus E n equals 1, that will become your light energy. Okay, so this is very important. So we're going to spend some time talking about these transitions. Okay, and basically, because of these different energy levels, okay, the light energy that comes out will be of a specific energy. Okay, so yeah, I just want to talk about excitation, de-excitation. When you energize an atom, so to speak, you will have transitions. You can actually supply it through heat, through electricity, whatever else. You can fire fast particles at it, you can fire light at it, whatever. But once you excite it, once you excite this atom, the way it de-excites itself is usually when you release light energy. Okay, light energy, or energy in the form of light. Okay, it's a particle / electromagnetic radiation. It's a dual nature, means to say it behaves as both of these things. So that's what that's the idea I want to get you into. You can actually look more into it here in the Physics Libre text. Okay, all this is Creative Commons. Okay, yeah, so I believe in a hydrogen, at least, there will be very specific energy levels. Okay, there will be very specific energy levels, and let's say your electron is up here. It's not just n equals 1, n equals to 2. There are many energy levels. All right. So depending how the electron de-excites itself, you will have a series of light coming out with different energy. Okay, your light will be emitted light from an excited emitted light of let me do this emitted light from excited hydrogen atom will have fixed energy. Okay, so that's a result of the quantum nature of these waves. So we have a fixed energy coming from these hydrogen atoms, depending on how we solve, because of the way the Schrodinger equation says that, hey, your energy levels are fixed. You cannot have any energy you like. So the light that that is emitted from a hydrogen atom will have fixed energy. And basically, as a result, energy and wavelength are actually correlated. So if you have fixed energy, it implies you have a fixed wavelength as well. Okay, your light coming out will be a fixed wavelength. Okay, meaning to say, basically there is a characteristic few wavelengths or spectrum, we could like to call it a characteristic spectrum that a hydrogen atom will have. Hydrogen atom will have when de-exciting. Okay. Okay, so where is that important? I believe over here, atomic structure. Okay. yeah, atomic spectra and X-rays. This is quite important. Okay, so this is basically what I'm trying to say here. Okay, now of course this is a very much more. Okay, this is Creative Commons. Okay, so I can use this. There's a license for it. Of course, I will credit. Who do I credit? Okay. OpenStax. Okay, OpenStax. Right. So basically, we have a very fixed pattern of energy or wavelength that comes from an excited state of a hydrogen atom. So I think it's called. Okay. So never mind. Forget that. Just look at this diagram here. Figure 8.62a. It's a very useful thing to have. Okay. Reference to have. Okay. So this is the more realistic look into these hydrogen energy levels, and of course you have SPDF. These pertain to different angular momentum that I was talking about. Okay. Right. So for hydrogen atom, you will have a very specific pattern of spectra that comes out from the excitation. So just want to get you familiar with this idea of excitation, de-excitation, so that you don't get confused later on. Now, of course, for sodium and mercury, you will have the same idea happening, okay, or same idea happening in the sense that there's a how do you say? Yeah, same idea happening that you have fixed energy levels, but the fixed energy levels will be very different from that of hydrogen. Okay, why is that the case? It's because the force fields, the electric force fields between this hydrogen atom and the sodium and mercury, all these force fields are very different. Okay, very different. So that's why you will have a different spectra for different atoms. Okay, different atoms have different electric field, and their force fields are different. Okay, so this will mean that the spectra. Okay, before you even talk about spectra, then because of your different electric field, your energy levels will be different. Okay, so these energy levels, they are remember we actually determine them usually by how we restrict this movement of the waves. Okay, the way we restrict the movement of the waves will determine what wavelength is allowable. Okay, and this restriction is due to the force fields, electric force fields are in place, or in the case of a nucleus, the nuclear force fields, or the strong nuclear force. Okay, so these energy levels are determined by the force fields, and therefore your energy level is different when you change the force field. Okay, energy level is different when you change the force field, therefore your wavelengths, okay, wavelength, okay, spectra is different. Okay, so most of the time when you have electron transitions, that means electrons going from high energy level to low energy level, you will have light that comes out of a particular color. Okay, there can be UV light, there can be visible light, so on and so forth. Okay, UV light, visible light, so on and so forth. Okay, and these are due to the strength of the force field, in this case, electric field. Okay, what happens in the nucleus? Okay, what happens in the nucleus? In the nucleus, okay, the strong nuclear force, we call this a strong nuclear force. Why is it called a strong nuclear force? Because there's a weak nuclear force as well, but we have not gone into that yet. Okay, so in the nucleus, the strong nuclear force is easily 1 million times stronger. Okay, so this is 10 to the 6. Okay. Or rather, okay, I should not say the strong nuclear force is 1 million times stronger. I should change the wording. Okay. Maybe I'll just say several orders of magnitude stronger. Stronger. Okay, such that the energy levels level difference is about 1 million times more. Okay, about 100,000 to 1 million times more. Okay, pardon the handwriting. So let's put this for scale. This is kind of a joke. Not joke. Okay, this kind of laughable, but this is energy of electrons. We use electron volt as the unit of energy. 1 EV equals to 1.602 times 10 to the minus 19 joules. So that's 19 0.0000 like 19 times, you know, that's how much. Okay, so 1 EV is this much. Okay, you see the hydrogen atom will have about 13.6 EV tops of energy. So hydrogen is about 13.6 hydrogen atom. When you talk about the nucleus, okay, so these are electron transitions, electrons. Electron transitions, they're about this much. Nuclear transitions, okay, they're not just EV, they're like MEV. Okay, so I'm not going to draw to scale because it's going to be many times. So okay, I should put MEV. Okay, these are in KeV to MEV, like usually in the MEV scale. That's how big they are. It's a huge difference. So let's keep that in mind. When you have nuclear transitions, so instead of electron, let's say going from high energy level to low energy level, you have protons this time. You can have protons at high energy level and they go all the way down to low energy level. And they will, of course, release energy in the form of light. Okay, what kind of light is this? Okay, it's no UV light anymore. Okay, UV light is too low energy for nuclear transition. We have gamma rays. Okay, gamma rays. So if you are wondering where gamma rays come from, they actually come from some of them, not all of them. Some of them come from this nuclear energy, nuclear transitions where protons or in some excited state, they de-excite and they have to release energy in the form of light. So they release energy in the form of gamma rays, and this is why we have gamma decay. Okay, gamma decay. So why some nuclear I guess radioactive elements, why do they release gamma rays? This is the reason. Okay, this is your first taste of from this Schrodinger's equation, how did we even come into nuclear physics in the first place? Okay, so this is radioactive decay. Okay, there's the decay law and everything, but okay, where is it? Nuclear reaction, yeah. Okay, all these nuclear reactions, they're very heavily governed by Schrodinger's equation. So you see, hold on. So you see this part about gamma. So it's a gamma, yeah. Gamma decay. So it says a nucleus in an excited state can decay to a lower level state by emission of a gamma ray photon, and this is known as gamma decay. This is analogous to a de-excitation of an atomic electron. Okay, this is one of the most important decays that you have in nuclear physics. So the whole reason why I was going so much about Schrodinger's equation is because I want to segue us into this very basic idea of energy absorption and release in the nucleus. Okay, so same idea, we have fixed energy levels because of the nuclear force fields. And of course, these protons, they actually vibrate in a waveform similar to electrons as well. And then it could be individual protons de-exciting itself, or the entire nucleus will have some sort of energy levels as well. Okay, because you don't just have one proton only, you maybe have 80 plus protons, and sort of it's there are many ways to store energy. Okay, so that part will come later, because yeah, previously we only talk about hydrogen atom where there's only one electron, and that's a oversimplified idea of these decays and de-excitations. Okay, but it does give you a general idea of what's going on. That's why we like to deal with hydrogen atoms. Once you start adding more and more electrons, your force field will start to change, and then things become complicated. Okay, so but that's the basic idea. That's the basic idea. So so I just wanted to get you a little bit into how all this Schrodinger equation lends us into the world of has implications in the world of nuclear physics. So we are getting into the nuclear physics realm already. Okay, so welcome to nuclear physics. Yeah. So anyway, one more note. This is not to scale. Not to scale. Okay, so if the energy transition is this much, right? Maybe this is what 1 mm. Okay, this is maybe I don't know, how long is this? 10 cm. I will actually need to really draw this to scale. I'll probably need to okay, maybe this is what, let's give or take this is 100 times, right? 100 times. Just a ballpark estimate. 100 times the length. I think that's agreeable. Yeah, 30 to 100 times maybe. I don't know. But hey, we are looking at mega, right? Mega is actually 1 million times. So how many pages would we need? Okay, how many pages would we need to draw this? How many pages would we need to draw this to scale? Okay, how many pages would we need? Okay, so if this electron transition within hydrogen is like 1 mm wide, and then we are looking for this energy levels transition. If you want to draw this to scale, and this from this 1 mm here, this maybe is about 100 times as long. Let's just give it a ballpark estimate. 100 times as long. Okay, 1 million is 100, so this is 10 to the 2, and then we need 10 to the 4, so 10,000 pages. Okay, so we need 10,000 pages of this energy transition in order to draw this to scale. So this is just to give you how much energy difference we are talking about here. If this is electron transition, the nuclear transition is easily about 100,000 times to 1 million times more, just to give you some scale. So you need about 10,000 pages to actually draw this to scale. I want to just introduce you to how much energy we are dealing with when you're talking about nuclear. Okay, nuclear energy is just that much more. Okay, so over here I only have what another 20 pages of white space. Okay, 20 other pages of white space. 20 pages, yeah. So you 20 pages, I will need 5,000 or 500 documents. Am I doing the math right? 500 PDFs like this just to draw this how much energy is to scale. So nuclear energy is super energy dense. Okay? So that's what I'm trying to say here. Nuclear energy is about 1 million times more dense. More dense than the electron energy. Now, what implication does this have? Okay, a lot of your electron energy is being stored as chemical bonds. Okay, so when you burn fossil fuel, okay, all of this is actually electron energy. Fossil fuels, when we talk about chemical reactions in a battery, right? All these are stored as chemical energy, and the basis for chemical bonds is actually electron interactions between atoms. So, yeah, you have mass for mass. You can have 1 million times the amount of energy within the same nuclear fuel as compared to coal, for example, or oil, or natural gas. Okay, so the take-home message I want you to get is nuclear energy is super dense. It's super dense. Okay, and it's all because the strong nuclear force is that much stronger than electron forces or the electrostatic force, and that's why you have these effects going on. Okay, quite just want to give you the idea of scale. So finally, yeah, after all this discussion of Schrodinger, we are finally getting into how it starts to impact nuclear physics. I hope that this will help you understand a little bit more about what's going on in the nucleus and how we can sort of have certain mental model of what's going on here, so that's less confusing. Okay, and this is just the beginning. This wave nature of matter will permeate almost everything we have to think about in nuclear physics, and we have to look into all these discussions next time. Okay, but I hope this is insightful. It gives you some idea as to what's going on. Thanks for watching. I'll see you next time. Bye bye.